Hello. Okay. Good morning, everybody. How are we doing? Almost halfway through the first week. Good job. Okay, so I guess maybe we can start off with a little summary and maybe just like if I can maybe I'll call on people just to have good. JJ, would you like to give us a like one sentence summary of what we did last time?
We did the definition of groups
Perfect.
for like operations where set, it's closed under a set.
Perfect.
Those rules.
Perfect job. Thank you very much, JJ, for being my guinea pig. Excellent, excellent. Okay, wonderful. So I'll let you guys ask questions if you have any. But yeah, we just basically give the definition of a group and some examples. And basically today we're going to be working through a bunch more examples. And actually, JJ brought up a good point with the definition of a group. And this is something I didn't really emphasize last time, but there was like a question on it. That a group should be a group is a set and an operation, right? It's like this pair. And that set should be closed under the operation. And of course, the operation is associative and the group has an identity for that operation and has an inverse. We didn't specifically say in this definition that Dumbin and Foote gives that the group is closed, which means if just as a reminder, to be closed, it means if you take any two elements of the group and you perform the operation, you don't jump outside of the group, right? So they don't specifically say that in this definition. It's kind of hidden in their definition of a binary operation. So Dumbin and Foote defines a binary operation to be a function on the ordered pair, or the Cartesian product G cross G to the group again. So it's because that image of that binary operation star has to end up in G. That's where we get the closure from. So yeah, thank you, JJ. That was a good summary because we do need closure, and that was a point that I wanted to make on the group, but it's not explicitly spelled out here. So good point. Okay, good. Any questions lingering from last time that I can address before we dive in? Okay, I will plan to do like sort of like impromptu, whatever, like recitation-y type thing. We can work through some problems today at 3:30. I actually ended up moving this time because they moved the junior M seminar, and so I don't want it to conflict. But I'm thinking maybe like Tuesdays at 3:30, but I'll send out an email and you guys can let me know if that's like a problem or something. Like, Tuesdays at Tuesdays at 3:30. I think GSS is 2:30 on Tuesdays, so after GSS. So let me know. Anyway, I might, first week, always these things float around. So yeah, but today I'll do it today because that was the plan. So great. Any other questions or anything before we get going? Okay. So great. So we talked about a group. We talked about abelian group means it's commutative. A couple other things that we should talk about when we're talking about groups is the order. And there's two ways or two types of things that the word order could be applied to. One is just the element in a group. And so if I take some sort of element like X in G, we call the order of X the smallest power. So it's the smallest integer or positive integer, so that x to the n is equal to whatever your identity was, right? So if I apply the operation n times, I should get the identity. So of course, if I raise x to some bigger power or some multiple of n, I will still get the identity. So this is the least such power. And if there's no such power, then we say that the order of x is infinite, okay? So we can apply the word order to an element, right? So that means how many times do I apply the operation to itself to get the identity? And we can also apply it to a group. And so the order of the whole group is just going to be the size of the group, which I don't think they defined here, but I'll just say that. Yeah. And I'll just say the order of group G is the size of the set G. So there's two ways you can use that word order, one to apply to an element and one to apply to the whole group. Okay, and so your book usually denotes it with this like absolute value sign, so as not to be confused with absolute value when that does apply. It doesn't usually come up, but sometimes we'll use this like ord x instead or something like that. Okay, so some examples. So basic boring examples. If I think about what the order of the identity element is, well, I just can raise that to the first power. So that's the smallest power that gets me back to the identity. So the order of that thing is just 1, right? And in fact, if A is not equal to the identity, then the order, then the order of A can't be 1, right? So that the identity is the only element that has that feature. Okay. Okay, so we had a bunch of examples of groups we talked about last time. We talked about like the integers and the real numbers, right, being groups under addition. So for most of the elements in the integers, say if I'm thinking of the group of the integers under addition, most of the elements are going to have infinite order, right? Like 2, if I add 2 to itself, it's never going to get me back to the identity, right? And no matter how many times I do it. But there's a couple, well, of course, 1 has order 1, right? Because it's the identity. So in the integers, so let's see, the order of 1, of course, is 1. And sorry. Oh, I'm sorry. Thank you. 0. Good catch. Okay, yes. Thank you. Good catch. Yes, the identity is 0. Very good. Good. And in fact, everything else, sorry, yeah, I was confusing myself. Everything else is going to have infinite order, right? Because 1 will also have infinite order, right? So there we go. Sorry about that. We are, and this is true, and it doesn't matter if I'm looking at R, C, the rationals, or the integers, right? Like I think everything else will have infinite order. This is all under addition. Thank you. Let's see. If I'm looking under multiplication, then thank you. If I'm looking under multiplication, I have to be a little bit careful, right? Because Z isn't a group under multiplication. I have to remove 0, right? Because 0 doesn't have a multiplicative inverse. And in fact, actually, I should be even more careful. This is not a group under multiplication, right? So let's think about Q remove 0, right? Q remove 0. This is a group under multiplication, I think. Yep. Got all my inverses. We're good. Let's see. Now my identity is 1. So order of that thing is 1. What about 2? What's the order of 2? Infinite again, right? So here, so like order of 1 is 1, 2 is infinite. Is there anything that's not going to have infinite order? -1. Very good. Or 1. Yeah, exactly. So the only thing is -1 is going to have order 2, right? Very good. Okay. Great. All right. So like a less kind of silly example. Let's think about Z mod 9Z. So again, there's no cross here. So this thing is not a group under multiplication because there are some elements of Z mod 9 or the congruence classes mod 9 that don't have multiplicative inverses, right? Like 3 doesn't have a multiplicative inverse because it's not relatively prime to 9. So this is always assumed to be under addition. So if we're thinking under addition, let's think about what the order of some of these elements are. Well, under addition, I can think of the order of the identity, of course, is still going to be, oops, sorry, the identity is 0. The identity is going to be 1. And what about the order of 1? Yeah, I think it's going to be 9, right? I'm going to add it 9 times and that's going to get me back there. Is every other element going to have order 9? 2 will have order 9, I think, right?
Just the one.
Yeah, just the ones relatively prime. What about 3? What is the order of 3 here? 3, very good. And so the order of 3 here is 3, so we can test this out. 3 plus 3 is going to be 6. Add 3 one more time, that's going to be 9. So that gets me back to the identity, right? So this is 3 plus 3 plus 3 is equal to 0. Good. And similarly, I think with 6, right? 6 is also, you can check that 6 should also be an element of order 3. 6 plus 6 is 12. Add 6 again, that's 18, which is 0 mod 9. Okay. And maybe one more example. Questions so far? Okay. Great. So now let's look at something. Now, when I put the cross here, I'm talking about the group of units, right? So this is the units or the things with multiplicative inverses. So this is going to be, in this case, all the stuff relatively prime to 7, which is most of the things since 7 is a prime. So here we're just really throwing out 7. And that's it, right? And this is assumed to be under multiplication. So last time. Okay, so under multiplication, let's see. We have the identity is 1, right? So of course the order of 1 is going to be 1. What about the order of 2? Two times 2 is 4 times 2 is what? 3? Yeah. Okay, wait. So 2 times 2, I'm now checking myself. 2 times 2 is 4, times 2 is 8, and that's 1 mod 7. So we're good. Okay, great. Thank you. Good. So 3, and we could check, say, order of 3. Let's say 3 times 3, that's 9, which is really 2 mod 7. So, oh God, this is too many to do in my head, but maybe you can take a minute. I don't think it can be 4. Let's see.
Oh, yeah.
I think it's 6. So you can double check me, but I think it should be 6. And there's a cheat here that I'm using in my head that we'll talk about later, which I think has to do with Lagrange's theorem, but which says that the order of the elements, we'll see this more explicitly later, but the order of any element has to divide the order of the group. And we said the order of the group is the number of elements in that group. How many elements? What's the order of this group? 6, right? There's 6 things in here. So the order of each of the elements had to divide the order of the group. So I knew it couldn't be 4 because 4 didn't divide 6, right? But 6 does, 3 does, 1 does. And you'll notice that happens for these other groups as well. the order of this group is 9, right? It has 9 things in it. And the order of every single one of these elements divides 9. Seem good? Okay. Cool. So just a helpful trick at this point, but it works. Okay. Any questions about order or anything like that so far? No? Okay. Great. Okay, so as I said, we're going to continue talking about examples of groups. So one of the first examples that you're maybe less familiar with from other contexts is the dihedral groups. And so this is a nice geometric example. So the elements of a dihedral group, which we denote with a D2N here, these are elements the elements are the symmetries of geometric objects for these. So these elements are symmetries of geometric objects. And so specifically, so these geometric objects are going to be regular planar figures. And so specifically when I'm talking about D2N or the dihedral group of order 2N, this is the set of symmetries of a regular n-gon. A regular n-gon. So what does that mean? Well, an n-gon is just, the n is telling me about the number of sides. Regular is meaning that they're equal length. These are, so the 5-gon, of course, is just like this regular pentagon with 5 equal sides. The 4-gon is just a square, right? The 3-gon is just the equilateral triangle, right? That's what we mean by n, right? Just take whatever number of sides you have. And so these are the rigid motions that we can make for whatever this figure is. Okay, so here let's look at an example just to kind of see how this works out in practice. So here's my 5-gon, right? It's a 5-sided regular figure, as regular as I can draw it by freehand. There's 2 ways that I can rotate, or I cheated. I can try to reorient this figure or give symmetries of this figure by using rigid motions, right? So one of them is that I can rotate, right? So let's say I take my figure here and I'm going to label the vertices just so that I can keep some sort of notion of what I'm doing when I'm rotating. Okay, so first thing, well, I can do the boring rotation, which is to just not rotate, right? So that's the identity rotation. The next thing I can do is I can move every vertex 1 to the right. Ooh, and I didn't draw it that regularly, so it looks a little bit lopsided, but we do what we can. The next thing I can do is I can move it 2 to the right, right? I can just move each vertex 2 to the right. Not perfect, not rigid, because again, my freehand is not ideal. And then I notice, okay, I could move, let's see, I can now move, let's see, this one, I moved 1 to the right. Here I moved 1 2 to the right. I could now move 1 3 to the right. Let's try to do that. See if it works. Ooh, bless you. And 1 would end up like over here, I think. Probably would work better if I just relabeled them, but we're doing a visual experiment here. Okay, and then the last thing we can do is I can move 1 from this thing, instead of moving it 3 to the right, I can move it 1 2 3 all the way to the right. So I move 1 to where 5 was. Great. Okay, so these are my rotations. And like I said, you probably would just relabel it. But all I'm doing is rotating where the 1 is, right? Or where everybody is. Okay, so I can do these rotations. That's one rigid motion I can do with this this pentagon. The other thing, what's the other kind of thing I can do to keep, what other kind of symmetries do I have in this? Yes. What's the word for this? Reflections. Very good. I like the dance moves more, but it's hard to write them down. So swish, swish, or reflections. Okay, so great. So now there's a bunch of different ways I can try to do the reflections, right? So these were all my rotations I had. I can take this thing and I can reflect through this one vertex that I had, and that gives me one reflection. Right, so if I do that, and I pick this guy up, and I put it here, and I reflect upon that guy, what it does is it now swaps 5 and 2 and 3 and 4, right? You should probably relabel these so they're legible. Great. So this gives me one reflection, right? And you'll notice that this reflection, this symmetry or whatever rigid motion didn't give me any of the things that were up here, right? So, oops, and I messed something up. This was 4, 5. Right. Okay, so I could reflect between around this axis here, but I could also reflect upon around the 2 axis instead. So if I were to do that, if I were to reflect upon this about this axis, that would swap 1 and 3 and 4 and 5. So 2 stays fixed, and then 1 and 3 swap, and 4 and 5 swap. I could reflect through the 3 axis, and that thing stays fixed. And what I swap is 2 and 4, and 1 and 5, I think. And then I could swap, or I could reflect about 4 here, and that would swap 3 and 5 and 2 and 1. Swap, sorry, 3, 5, 2, 1. And then last but not least, I could reflect through that 5 vertex there. Right, so if I reflect through 5, I swapped 4 and 1 and 2 and 3. So this is 4, 1, 2, 3. Okay. Whew. All right, so I think that's all I got. I think that's all of my motions, unless I missed something. But I think we're good. Okay. Did I do that right? 5, 5. Okay, great. Cool. So any other type of motion that I would do on this 5-gon is going to get me something that's not exactly symmetric from where I started. And so we can think of these. So if I want to now think about this group, D10 in this particular example, or D2N, the set of all of these rigid symmetries, I want to think of this, be able to think of this as a group. And so, we'll first think about what the elements of this set are. Well, the set of symmetries, well, it's going to be the set of the rotations and the set of the reflections, right? So D10 is really the set of these 10 rotations and 5 rotations and 5 reflections, right? So I have these rotations, and maybe I'll call a rotation by, oh God, whatever 360 divided by 5 is, but like this 1/5 rotation, I can call that R, right? So this is, so I have the identity rotation. I, of course, have R. Or I could do apply R twice, right? So this is rotate by R. And then doing this would be rotate by R squared, and so on. Maybe I should do this in different color. R. And this is like R squared, right? Which is just applying R twice. I could apply R 3 times, right? Right, up to, and I can do this all the way up to n minus 1 times, because once I do it the nth time, I'm going to get back to the identity, right? Okay, great. Great. And then I also have these reflections S. And one thing you might notice about the reflections, is that we could choose all these different, the way we wrote it is we could choose a different vertex to do the reflection about. And maybe I wrote it in a different order that it's less clear. Oh, I did. Bummer. Okay, so let's see. 1, 2, 3. One thing to notice is, okay, so here we've listed all of our rotations individually. But what I could do to try to like categorize how these reflections work is instead of just choosing a different vertex and then reflecting about that vertex, what I notice is if I first, let's look at this reflection. If I instead applied our, let's see, I think it was, I'm reflecting about 3, right? Or sorry, oh, dang it. Sorry, one second. What am I trying to say? Is it this one? No. What was I trying? Oh, I'm sorry. I was trying to look at this one. Okay. Here, I fixed my vertex and I reflect about 1. That's what I'm trying to say. Sorry about that. Right, that's how I get from here to here. So instead of just picking a different vertex on this figure, what I could do is I could think of first rotating, and I see how many rotations do I have to do if I kind of were to choose the same axis and reflect about the same axis. So notice, if I was going to get to this reflection, what I could do is I could instead rotate, 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 and then apply reflection, and I get to this figure, right? So whatever this reflection is the same as applying 1, 2, 3 r cubed, and then reflecting about the same axis. Okay, so all of these reflections are really just like there's one reflection. I think of just reflect upon whatever this vertical thing is, and I'm just going to do rotations and then reflect. That's how I'm going to categorize them. So if I call reflection just over a fixed axis S, then all of the reflections really look like S, or I could rotate once and then apply S. So I'm just going to call this movement S. Or I could rotate twice and then apply S. So I think here, let me see if I can find it. This guy. Yeah, because this guy is like rotate once and then apply S. Is that right? Yeah. And then this guy is like rotate twice and then apply S. And this guy is like rotate 3 times and then apply S. And then, rotate 3 times and then apply S, function composition. And then this guy is like rotate 4 times and then apply S. Great. So all the way up to whatever, apply S. Great. And I notice this gives me my n different reflections that I could have. Okay, hope that makes sense, sort of. Sorry, maybe my picture was less helpful. Great. So, so what is my set? My set D to N, I can kind of, if I want to think of listing these objects, well, I have the identity rotation. I have all of these rotations by R to the N minus 1. And then I also have apply each of those rotations and then apply S, right? So apply S to the identity rotation, apply S to the rotation R1, apply S to R squared, and I have S to the. And I notice that this group, D2N, is always going to have order 2n, or the size of that group is always going to be 2n. That's why we use that notation. So when we looked at our example of the 5-gon here, this is a 5-sided figure, and there are 10 different rigid symmetries, 2 times 5 different rigid symmetries of the 5-gon, right? And so that means there are 10 elements in this group. Okay, so these are the elements in the group. To see this, I'll just say, I think a more rigorous proof is, or maybe not even full proof, but more rigorous explanation is on page 24 of Dumma Input, if you want to see this kind of written out in more detail than I said out loud. Okay, so these are the elements of the group, but there's some other relations that we should maybe observe about this thing so far, but I should pause for a second. Are there any questions? Sorry, I just ranted for a second. Okay, so one thing we already kind of noticed was that none of these, applying the reflection once didn't really give me any of the rotations, right? So the reflections and the rotations are always going to be distinct. So one thing we noticed that we said out loud is that S does not equal R to the I for any I. Cool. So the reflection, if I just do a reflection, it's not going to be already taken care of by some rotation. Another thing that we sort of said out loud. Oh, no, sorry. Another thing that we might notice is that, let's see if I can illustrate this properly. Let's see. This group is not exactly abelian. So what does it mean to be abelian? It means that we can move the elements back and forth, right? And, swap the order of operations, right? So, of course, I can apply, if I were just looking at the rotations, that thing's going to be abelian, because if I write apply r cubed and then r squared, that's going to be the same thing as r cubed r squared. That composition is going to work out just fine. But the worry is when I start moving reflections and rotations. If I look at something like s times r, does that equal r times s? So here's a question. Does s times r, or applying r first and then s, give me the same thing as applying s first and then r? That's the question. And I told you no, but I guess it could be true in certain examples, but shouldn't generally be true. So let's just pause for a second and think. This is the question. Does applying r first and then s give me the same thing as applying s first and then r? Okay, so this is what we said was applying r first and then s. So what if instead we first applied s, that gets me here, and then I rotate? If I rotate, I get, yeah.
Question.
Yeah.
So how can you define the reflection as reversal? Because
Rigorously?
like we use different axes to reflect the animal.
Yeah.
So
I think.
should we have to define s with the same axis, like a
Yeah, so that's what, for this s, we're just going to fix an axis, is the idea.
But I think we use different axes because the axes are depending on the vertex number.
Yeah, so okay, yeah, sorry. When we wrote it up, so there's two ways you could define it and they're equivalent, I guess is the point, right? So when we did an example, like the natural way that you might just, if you started from this thing, you could just say, let's just choose a different axis, right? Every single time. And that's kind of how we did it to start with. And I maybe made this confusing, but the point is it is equivalent to say, fix an axis. There's only one reflection upon whatever axis you chose. And then to generate all of the other like pieces of all of these other reflected things, you're going to first apply a rotation and then do that same reflection of S. So there's only really like one reflection upon one axis that you're fixing. So you fix something like, fix the upper leftmost or something silly, which is kind of hard to define rigorously, I guess, if that's your point. And it is equivalent to say, reflect upon every axis, will give you all the same elements of the group as rotating first and just fixing one axis. Does that answer your question or make sense?
I think the fourth, the fourth one in the reflections, so like 2, 1, 5, 4, 3, that one is, it can be represented by SR, because if we fix the axis, so.
Yeah, so good. Okay, wait, so maybe that's also your thing. So this is, so you're saying, okay, that was a different, I thought a different comment, but we'll be just, you're saying this. Is that what you're saying? Oh, did I mess something up?
I mean, if we choose the axis with with respect to vertex 1, then if we rotate first, then I think the axis also rotate. Yeah, so isn't it?
But when I'm saying this, then you don't rotate the axis with the figure. The axis is independent of the rotation. Is what I think was what S is. S is just like, this is always, and you're gonna rotate stuff around whatever this axis is. The axis is independent.
Can you define D2 and by 2 ways, like a axis can be rotated by rotation or just independent of the rotation?
So yeah, so you can do it. So you can do it moving the axis. But then you would have, you write your reflections as differently, like you'd say all of these are different elements. And the nice thing about this presentation is that you can, so you could write a presentation that way. I think that's fine. If I understand you correctly, I think you miss out a little bit on some of the structure, and like these all now look like very independent elements where they're actually sort of related to the rotation. If that's the only thing that I think makes it a little bit nice, is that you can see the relationship between reflecting and the rotation, I guess. But yeah, like I think the way you're saying it, I think you would have to kind of define these as completely different elements. And then you'd say, oh, look, I have 10 different elements. I'm going to call this thing what? Does that make sense?
Yes.
So I think there's lots of ways you can define it. And in fact, I think there's a couple exercises in the book that have you write the presentation for this group in a different way. I don't remember if I signed them exactly. But this is the canonical one, is think of the axis as whatever you chose it to be, just fix the axis. And then there's going to be however, n different rotations always, because you can always just swap, do a little cycle of your vertices. And then just fix the axis and do each one of those and whatever reflect upon that axis. Good, thank you. That was hopefully helpful. Good question. Okay, so wait, maybe this is not, okay. Okay, so the question then is, hopefully we're clear. So the question then is, if I do a rotation, is that what I want to say? If I do a rotation, yeah, if I do R and then apply S, is it the same as S and then apply R? So I do R. Wait, maybe I'm reading it backwards. Well, let's see. So I do R. And then applying S would mean swapping these things. So that puts me here. So I think that one works, right? Yeah, so this one is equal to SR. Am I crazy? Okay. But is that a fluke? Did I do something weird? Shoot.
Wouldn't RS be like the SR to the fourth? It would,
Oh wait, yeah, did I do that backward? Oh, I think I just like confirmed the same thing. Hold on, sorry. Whoops. Okay, so this is RS. We already said that. So, okay, yeah, so what if I do S? That's what I'm trying to say. Thank you. What if I do S, which is this, and then I rotate this thing? Okay, if I rotate this thing, that puts a 2 up here, right? So it should be 2, 5, 2, 1, 2, 1, 5, 4, 3. Would we see that? Or is it? SR4. Thank you. God, there she is. Oy. Okay, good. So there we go. I was like, this doesn't seem right. I just looked, I verified that the same thing was equal. Good. You need a bird's eye view for this thing. Okay, perfect. No. Okay, so the answer was no. Good. Okay, and in fact, what is the relationship that should hold? Is if I have SR to some power, that should be, they don't exactly commute, but I get, I go the opposite direction. It's the same as applying the reflection first and then going the opposite direction by rotation. Did I do backwards? Ah, thank you. Oh, that's why. Wait, no, I think this is all right. This is right, RS, but this is R to the fourth S, like this. Is that what I mean? No?
S different to
R.
R
On the one above you said something.
Oh, thanks.
S different to R to the.
I mean, the second one,
Yeah, the second
this is done equals R to the.
this.
Oh my God. This is, am I crazy? Okay, what am I saying? Oh, yes. Oh, I'm sorry. Yeah, that should have been a not. Is that what you're saying? Oh, God, thank you. Jeez. I just really was not seeing what you were saying. Okay, wait. So this is fine. So the answer is no. Okay, we agree with that. Whew. And this is what we should be saying. Good. And then the other okay, so let me just say. Okay. Okay, let me write things down and then you can tell me if I said something false still. Okay, that's what I mean to say. Okay, do we agree? Thank you. Ah, okay. Okay, perfect. Okay, great. Question. Okay, so doing this little nice investigation, we have like D2N represented by a set. But this set alone isn't really telling me about this relationship, like between R and S, and how these things relate, right? It tells me these are the distinct elements, but it doesn't tell me what happens with this composition if I try to, switch the order of R and S and things like that, right? And so this is where what we can use is a more explicit version of a group representation that involves not just the elements, but some relationships between them. Okay, sorry, was there a question I should clarify?
Is that a negative I or is that just?
It's a negative I. Oh, so yep, this is a negative I. And I said it before and I should have said this. So this is moving in the opposite direction. Rotating I times in the opposite direction. Does that answer your question? So if you chose your rotation to be clockwise, then it's rotate counterclockwise. Okay, perfect. Does that answer? Everybody good? Okay. So, okay. So a subset S of G with properties that sorry. So there's two. So to give a nice full presentation, we sometimes so the elements R and S that we've listed above, we can think of as they're examples of generators of a group. And so so a generator of a group is a subset of that group with a property that I can take finite products of the elements and get the rest of the group, right? And so we saw that I can get every single element of D2M by just taking multiples of R's and S's, right? And so, so for example, D2N is always generated by R and S, right? Or the integers, as an even more basic example, are generated by the element 1, right? Because I can add 1 to itself. Of course, I mean under addition, obviously, because you can add 1 to itself as many times as I like. You know, apply inverses, well, and their inverses to get everything in Z, and same thing with D2. For something like the integers, this is really enough to tell me kind of everything I need to know about the integers. There's no other weird relations that are happening with the integers to give me a lot more about their structure. But for D2n, we saw we have this like, because this is like a nice commutative group, but for D2n, we saw this is not an abelian group. And so it was also nice to have some sort of relation that tells me, hey, what happens if I try to swap R's and S's, right? And so any equations like that in a group that the generators satisfy are called relations. They're called relations. And so, for example, in my D2n case, I have something like if I raise R, if I apply R to itself n times, I get the identity. If I reflect twice, I get the identity, right? And also, if I apply S and then R, it's the same thing as doing R inverse and then S, right? So those are some examples of relations, right? And so when I put, so these brackets always mean the group is generated by these elements as opposed to just being a set only containing those two elements. These are denoting that they're generators. I can give a full group presentation by denoting the generators. So I first list that set of generators, and then I would list all of the relations that hold. So that thing is called a group presentation. So for example, for D2n, one way of describing explicitly this full group is that I have two generators, R and S, because I just need to take multiples of those things to get every other element of the group. But sometimes, eventually, we'll get back to the same things. So for instance, if I take R and I apply it to itself n times, I get back to the identity. And same thing if I apply S and I apply it to itself twice, I get back to the identity. And then last but not least, you want to know what happens if I try to swap R and S. Well, it isn't exactly commutative, or it isn't exactly abelian. It applies the inverse to R. Okay, so you'll sometimes see these group presentations, again, generators and relations that they're going to satisfy here. Okay. Great. Questions? Sorry about that being a little more confused. Yes.
Why to show the two the same? Or we just like manipulate the relation?
Yeah. So to show that two presentations are the same, yeah, I think you'd want to be able to, well, so assuming you have, you'd want to show that you can get from one set of generators to the other, like that the sets are equal of generators. And then also, yeah, some sort of way of going back and forth between the relations. Yeah, that the relations are equivalent in some sense, or at least that you can get one for, yes, equivalent items as a set. Good. Other questions? Great. Okay, so we'll go into more detail about the symmetric groups next time, another really nice example, but we'll just kind of give some setup for it. So the symmetric groups are going to be the set of bijections of a set from a set to itself. So sometimes you'll see this, we'll usually be talking about the symmetric groups on just n elements and refer to them as Sn, but you could talk about the symmetric group on like any set, say omega, right? So we'll say omega is a non-empty set. So this S omega is the set of bijections from omega to itself. And the set of bijections means this is the set of one-to-one or injective and surjective functions. Right. Okay, so as a nice little reminder, to be an injective function, means that that if your outputs are the same, your inputs had to be the same too, right? So right. So no two different elements are going to the same thing. And F surjective means that everything in the range is being hit for each y in B. There is an, or sorry, I'll say an omega. There is an x in omega. So f of y is, or sorry, f of x is equal to y. Great. Okay. So thinking about all of these are just a set of functions, right? They're not, the things in the set are these maps, right? And this collection of all of these maps also forms a group where the operation now is function composition. So not multiplication like we would think, or addition, but function composition. If my operation is function composition, I'll leave you with one question. What is the identity element? The identity map. Yeah, the thing that leaves everything fixed. Good job. You're getting a fist bump. You need to return that. Okay, perfect. All right, I'll leave you there, and we'll talk more about the symmetric group next time. Thanks, guys.